Hello, and welcome to Agrosive Physics. Today is day 121, and what I'd like to do today is discuss series circuits. Now, we've already discussed Ohm's law, which is V equals IR, and the power and energy equations, which is P equals VI or E equals PT. Now, of course, there's other versions of the power and energy equation, but our standard is P equals VI. So we have two equations, V equals IR and P equals VI, that cover most of what we can use to find different variables in a circuit. Now, the most simple circuit you can have is a battery connected to a light bulb or a resistor. And in that case, what's going to happen is the battery is going to provide the push for the electrons, and those electrons are going to use up all their energy going through the component. When they're traveling through a resistor, all of the energy that was provided to the electrons by the power supply is used up. Now, if you have a series circuit, that's connecting more than one resistor or light bulb or some component in a row. And when you connect them in a row, you have a battery, then you have the first resistor or lamp, the second and third, and then you go back to the battery. And in that case, there's one path for current to flow. So the way that a series circuit is defined is it's a circuit where there's only one path for current to flow. Now, if there's a break in the circuit anywhere, what's going to happen is it's going to cause the rest of the circuit to fail. So many people who put up holiday lights experience that in certain segments of the light strings themselves. Now, you may have 100 lights, and there might be 5 different circuits contained in that 100 light strand. That means every 20 lights is a series circuit, and each of the 5 strands of 20 are connected in parallel. And for now, we're going to talk about series. In one of those holiday lights, if you remove a light bulb, what's going to happen is the rest of those 20 strands on that string are going to stop working. And that's because what you've done is effectively turn the switch off for that section. When you have a break in the circuit, the electrons don't have a way to flow past that. And what they'll do is stop working. The push won't provide any push anymore, and the electrons will just stop. So a series circuit is one single path for the electrons to travel. And if any of the light bulbs turn off, for example, if you have incandescent bulbs, you unscrew one, the rest will stop working. So you can tell if you have a series circuit if you remove one component and the rest stop functioning. Now, what we're going to talk about is how to use V equals IR in order to calculate different characteristics of the circuit. Now, when you have a series circuit, the current is the same everywhere in the circuit. And that's because there's only one path for the current to flow. It's as if there's one river and all of the electrons are in the same river, and they're all traveling at the same rate. So how do we find the current flowing through the different resistors or components? Well, the way we do that is use V equals IR. So if you know the voltage or the power supply, if you plug it into a wall, it's 120. If you connect it to some batteries, it may be 3 or 6 or 12. It could be even a variable power supply where you have a way to change what the power, the voltage is flowing through the circuit. In either case, the energy that's given to the electrons has to be shared by all the different components. Because what happens is the electrons get energized, they go through one of the components and lose some energy. They go through the next component and lose some more. And then they go through the final component, or if there's more and more, they go through the rest of the components. And by the end of all the components, they have to be back to zero. When an electron reaches the battery again, it has to be back to zero energy. Because what has to be the case is that it has no extra energized nature. It has to have no energy left. If it did, each time the electrons move around the path, they would have more and more energy, and you would have a situation where the energy would build up as you leave something on. That's not the case. In fact, all the energy needs to be used up each time. So, how do we find the current flowing through the circuit? Well, the problem is if you do V equals IR and you have different resistors, you're going to get different values for the current. So there needs to be a way that we can simplify the circuit in order to find the current. And the way we do that is we draw what we call an equivalent circuit. And the equivalent circuit is what the battery sees if we treat all the resistors or light bulbs as a single light bulb or single resistor. So we call that the equivalent resistance, and we combine all the resistors into a single one. The battery sees the single resistor or the series of resistors as the same thing. That's why we call it equivalent. It's the same as the original. So how do we do that? Well, we simply have to add the resistance values up. So in order to find the equivalent resistance, which I call Req, or you may call RT, sub T, or sub EQ, EQ for equivalent, or T for total, what you do is you add up all the resistors. We typically use 3 resistors as our standard series circuit. It could be 2 or 4 or 10, but for whatever reason, we've chosen 3 as our standard. And I think the case is if we draw a square or rectangular circuit, you have the battery on one side, and then each of the other 3 parts of the rectangle has a resistor included on it. So just visually pleasing. Now, if you have R1 plus R2 plus R3, that will get you your equivalent resistance. And when you have your equivalent resistance, you can draw that as a single battery or power supply and a single resistor. Now, in that case, you can find the current using V equals IR. Since you already have the equivalent resistance, what the battery sees, that's going to get you the current that is flowing from the battery through the resistors in conjunction with one another. So the way we do that is we add them together, and then we do V equals IR to find the current. Then we can expand the circuit back to its original and analyze each component separately. Now I think of this as an accordion method. And what we do is we simplify the circuit, we smush it together, we find an equivalent circuit, and then we expand it back. And we may have to compress it again and expand it back and compress it again, kind of like playing an accordion. So the accordion method will allow us to simplify circuits and then expand them back to analyze them. Now when we expand them back, whatever the current was flowing through the circuit originally is going to be the same for each component. So the current flowing is the same for the total from the battery. I1 equals I2 equals I3. So the equation for current after we simplify and then do V equals IR is IT, or IEQ if you want, equals I1 equals I2 equals I3. Now finally, as I said before, the voltage has to be used up by each of the components so that the electrons are back to 0 when they get back to the battery. So the way the voltage works in a series circuit is you add up all the voltages, and that should be the total that the battery provided. We call them voltage drops when they go through resistors because the battery provides a gain, so you gain energy at a battery, and then you drop voltage as you go through the components. So the equation is VT equals V1 plus V2 plus V3, very similar to the resistance equation. Now, if we happen to have a situation where we're dealing with an actual series circuit, I have a circuit here that is a 12-volt power supply, and then we have a 5 ohm, a 10 ohm, and a 15 ohm resistor. Well, what's the equivalent resistance of 5, 10, and 15? Well, you have 5 plus 10 is 25 plus 15. 5 plus 10 is 15 plus 15 is 30. So the total voltage is 30. The total resistance is 30. So if you do V equals IR with your equivalent resistance, you would do 12 equals I times 30. When you divide that, you get 0.4 amps. Now that is the same as the current flowing through the entire circuit. So if you expand it back using the accordion, we smushed it together and got 30, did V equals IR to get 0.4, expanded it back out, and we ended up with the I, which is 0.4, leaving the battery. Well, if you do that, what you can now do is say that I is 0.4 going through each of the components. Well, I is 0.4. And if you go 0.4 through the 5 ohm resistor, you get 2 volts. 0.4 times the 10 ohm resistor, you get 4 volts. And 0.4 times the 15 ohm resistor, you get 6 volts. Well, if you add 6 plus 4 plus 2, you get 12 volts, which was the original voltage flowing from the battery. So the voltage drops have to equal the voltage gain. This is basically conservation of energy. So in a series circuit, we have a couple of things that we need to worry about. First of all, we need to simplify the circuit in order to analyze it. And we do that by using the accordion method. We smush it together, find the equivalent resistance, do V equals IR. Then we expand it back out and do V equals IR again using the current and the resistance to find the voltage. Our final thing we could do, if we were asked, is to find the power. And in order to find the power, it would be P equals VI. You could even do I squared R or V squared over R at this point because you know all of the different characteristics of each component. So what I'd like to do in a typical circuit problem is I don't even look at the question. I always solve for all the variables I can, and then I look to see what they're asking for. Now, of course, on a state assessment, you'll want to be more efficient with your time. But for the beginning practice problems, find I, R, and V for every component. And then what you should do is find P, because a lot of assessments will ask for brightness. And if you have light bulbs, what you'll find is that the higher the power, the brighter the bulb. So even though it may be rated at a higher value with 120 volts, because it's sharing all the voltage between others in a series circuit, what you'll need to do is recalculate the power, and it may be less than what you originally were rated at. So series circuits can be quite complex at first glance, but if we remember to simplify them and then expand them back to analyze them, you'll find that series circuits are not that difficult if you know the proper procedure. I think at this point what I'd like to do is a full practice problem. The practice problem I just talked about verbally might have been difficult to follow because I was just talking about the answers. Now, if we follow a whiteboard sample, you'll be able to see how a series circuit can be solved with actual light bulbs. Let's take out the whiteboard now and solve that sample problem. Thank you. All right, now we're going to connect components in what we call a series circuit. Now, a series circuit can be drawn as follows, and I'll put resistors in this circuit for now. The power supply, and then each resistor in one continuous line. So there's only one path for the current to flow in this circuit. If we're doing conventional current, it would flow in this direction. If we're doing the electron flow, it would flow in the opposite direction. Now each resistor I'm just going to call R1, R2, and R3. We'll say V is the power supply. And that could be 120 volts or 6 volts or 12 volts, or it could be any value in between. Now, the important thing to realize in this type of circuit is that the current, because there's only one path, is constant. So I is the same everywhere. The problem is if you do V equals IR for each of the resistors and they're different values, you're going to get different I's. So you cannot use V equals IR with the setup as it states. What you need to find is the equivalent resistance. So you have to take every circuit and simplify it so that it's a single resistor. Now the way you do that, and we call this REQ, equivalent, or RT for total. Now the way we do that in a series circuit is I'm going to do RT, add up all the resistors, R1 plus R2 plus R3. Now when we do that, the voltage flows through this one resistor, the total equivalent resistance, and then all of the energy is removed. So the goal of a power supply is to energize the electrons. They flow through the, in this case, equivalent resistance, and then lose all that energy. And then they have no energy at this point, and they're just pushed through the circuit by the other ones coming from behind, and eventually get re-energized. And they go through the process over and over. The beauty is, if we simplify the circuit to look like that, the current flowing here is the same as the current flowing in this expanded circuit. So I like to think of it as an accordion. We simplify the circuit and then we spread it out, kind of like playing an accordion. We smush it together, simplify it in this form, expand it back out, and we have the original circuit. Now we can use V equals IR to calculate the current, the voltage drop in each. So we know the current flowing through each, and we can find the voltage drop. Now, the way the voltage works, the total voltage in the circuit is going to be the sum of the voltages flowing through each of the three components. And as we stated before, I is the same everywhere. But the only way to find I is by finding the equivalent resistance, simplifying it, and then expanding it back out. So you have the resistance is added together. The total voltage is the sum of the voltage drops. So the electrons are energized. They lose energy in each one, and they have to be back to zero when they get to this point here. And then the current is the same everywhere. And the way to find the current is simplify the circuit and then expand it back out. And it's the same in both of these because these are equivalent circuits. You're looking at the same circuit twice. So that's the theory behind the series circuit. All right, let's do a sample problem dealing with series circuits. And what we're going to do is connect 3 light bulbs from before. So I'm going to use the light bulb symbols. And we're going to plug it into the outlet. Now, when we connect light bulbs in series, they're not going to act as they would normally. Our electrical circuits in the house are connected in parallel. So when you plug in a 100-watt light bulb, it's going to maintain that 100 watts of brightness. The one thing that is constant, even if the power output will not be the same, is the resistance values. So we're going to use a 100-watt bulb, a 75-watt, and a 60-watt bulb. And we're going to see how they act when they're in series. The 100-watt bulb was 144, the 75-watt was 192, and the 60-watt bulb was 240 ohms. Now, when we look at this, if we did V equals IR for each, we'd get 3 different I values, and that's not how series circuits work. In fact, we need to find the equivalent resistance. In this case, we have to take the resistance of each and add them together. And then we can find the current flowing through the circuit. So the total resistance of this circuit is 144 plus 192 plus 240. And that gives us 576 ohms of resistance. So this right here is 576 ohms. Well, we have the voltage and the resistance in this simplified circuit, so we could find I using V equals IR. 120 volts, I, 576 ohms. 120 divided by 576 gets us a current of 0.2083 amperes. So the current here and the current in the original circuit, 0.2083 amps, will be the same. Now, if we have the current, we can do V equals IR to find the voltage drop through each of the resistors. 0.2083 amps times 144 times 192 and then times 240. So if we multiply that by 144, we get 30 volts. 0.2083 times 192, we get 40. And 0.2083333333 times 240, we get 50. So the 144 ohm resistor takes away 30 volts of the total. The 192 takes away 40 volts of the total, and the 240 takes away 50 volts of the total. Now, if we look at this, 50 plus 40 is 90, plus 30 is 120. That's the total voltage of the circuit. And remember, the electrons need to lose all their energy as they come back around. So the values have to add up to 120. Now let's see what happens to the power outputs of each. If we get rid of this little section here, we can find the power. Now power is V times I. And since I is the same everywhere, we can multiply 30 volts times 0.2083, 40 volts, and 50 volts. And we'll see which one is the brightest. So 30 times 0.2083 is 6.25, and that's watts. 40 times 0.2083 is 8.33 watts. And 50 times 0.20833 is 10.42 watts. So if we connect the 100, the 75, and the 60 watt bulbs in series, the 60 watt bulb is actually going to be the brightest. So this is the brightest. The 75 watts in the middle, and the 100 watt bulb will be the dimmest. So depending upon how we connect light bulbs, if we connect them in series, the brightest rated bulb is going to be the dimmest, and the lowest rated bulb will actually be the brightest. And that's how we can analyze a series circuit.